Hey guys, welcome to Electronics. I'm Gregory and today we're gonna learn about push-pull stages. We're gonna see the transition between class B, class AB and class A operation. First I'm gonna go to the whiteboard where I'm gonna explain the circuits and I'm gonna come back here to the bench to make some experiments. Let's go! So guys, this is the basic topology of a push-pull pair. We have two emitter followers here, a NPN emitter follower that will follow the positive cycle of the input signal and a PNP emitter follower that will follow the negative half cycle of the input signal. Why we would use this kind of circuit? Well, the push-pull pair can be used to deliver power to a load. So we can take a high impedance signal on the input and transform the signal in a much lower impedance signal that can be delivered to a very low resistance or high power, high current load. We know that the emitter followers don't have voltage gain, but it has current gain. So we have the capability of delivering much more power to the load. So how it works? It's very simple. The positive cycle of the input signal will be followed with the NPN transistor, the upper transistor. The signal will be present here on the base of the transistor, and the emitter of the transistor will follow the base signal. When the signal is positive, the PNP transistor is in cutoff region because the base is more positive than the emitter, so the transistor is not here. And we have a positive NPN follower. The voltage on the load will follow the input voltage. We don't have voltage gain, but we have current gain, because the current in the base is much less than the current that can be delivered on the emitter of the NPN transistor. On the negative cycle of the signal, this area here, the upper base will be negative in respect to the emitter of the NPN transistor. So this transistor will enter the cutoff region and will be out of the circuit. Now we have a PNP follower. The emitter of the PNP transistor will follow the base voltage. So we can follow the negative half cycle of the signal. When the input is positive, we have the NPN transistor doing the work, and when the signal is negative, we have the PNP transistor doing the work. The NPN transistor can source the current to the load, and the PNP transistor can pull the current from the load. This is why this stage is a push-pull output stage. Later, we will understand the purpose of these resistors on the emitters. They are crucial for the circuit to work on the real life. If you are smart, you are thinking that this circuit has a problem, and it has. We know that the emitter follows the base with a VBE drop. The emitter voltage is always less than the base, 0.7 volts less. This is the VBE drop, the voltage between base and the emitter. This also happens here on the PNP transistor also, but the base needs to be 0.7 volts negative in respect to the emitter of the PNP transistor. So what happens if the input signal is smaller than 0.7 volts? Well, the transistors will not turn on and we will get no signal on the output. If the input signal is, let's see, 0.4 volts here, 0.8 volts peak to peak, 0.4 volts positive, and 0.4 volts negative. We will have, on the positive cycle, we will have 0.4 volts here on the base, but we need at least 0.7 volts to the transistor conduct, to the base conduct. So this transistor will never turn on, because here we will be at 0 volts as the load is pulling this node at 0 when the transistor is in cut-off region. When the signal becomes negative 0.4, this transistor will be out, and this transistor also would be out, because we need at least negative 0.7 volts here to get the emitter junction forward polarized correctly here. So signals with amplitude smaller than 0.7 volts peak will not appear on the output because the transistors will stay in cutoff region. If you increase the input voltage, let's say that now we have a signal here that has 2 volts peak to peak. So negative 1 volt here and positive 1 volt on the positive cycle. Now the transistors will conduct. So on the positive cycle we will have here plus 1 volt, but we have the VB drop on the emitter, on the base emitter junction. So on the output we will have 0.3 volts. Because VBE is 0.7 volts. On the negative cycle, we will have negative 1 volt on the base of the PNP follower, and the output will be negative 0.3 volts, because the VBE here is negative 0.7 volts. So this is kind of working, but really not, because the signal is following, the output is following the input, but you have a drop, and you have an area here. This area here will not be active, because here the signal is below 0.7 volts. So the output will not be this. We have some area here where the two transistors are in cutoff. This is distortion. This is crossover distortion. Distortion when the transistors cross the 0 region, the 0 volt region. So this area here is distortion that will impact the performance of the output. So we can see that the output is not following the input correctly. This is the clever way you get around the problem of the VBE drop. We can use 2 DC supplies in series with the signal here. So we have an offset voltage equals to VBE. So the base voltage of this transistor will always be 0.7 volts greater than the input signal. The base of the PNP follower will be always 0.7 volts below the input signal. So if the signal is 0.4 volts, here we have 0.4 plus 0.7, so 1.1 volts. We get the VBE drop of 0.7, and here we have 0.4 volts and 0.4 volts on the output. If the input is in the negative cycle, we have negative 0.4 here, we have negative 1.1 volts here. Here we gain a VB drop, so it's minus 1.1 volts plus 0.7, and here we have minus 0.4 volts. So now the output is following the input precisely. In the output now we have an exact copy of the input signal. The name of this class of operation is class B. This is class B of operation. In class B we are compensating the VB drop with these power supplies here. So now for half the cycle, the NPN transistor will do the work, and for the other half of the cycle, the PNP transistor will do the work. This is class B of operation. But it's very hard to make this work on the real life, because the VBE voltage can change with temperature, with aging, with the load current. So it's very difficult to make the precise voltage here to compensate the VBE effect. Let's say the VBE changed to 0.66 volts. Now we need to compensate with 0.66 volts. And even the VBE of the two transistors will be different. So it's very hard to make an exactly precise compensation. One thing we can do to improve in this respect is that we can compensate with a little more than VBE. A voltage little greater than VBE. So let's think we'll use 0.8 here and 0.85 and 0.85 here. Now we are compensating with more than a VBE drop. So the transistors will conduct a little more than half the cycle. Yeah? Because even with 0 volts here, let's think, if we have 0 volts here, we have 0.85 here, minus 0.7, we have here 1.15 volts. Okay, VBE, standard VBE for development is 0.7 or 0.65. We have 0.15 here. On the negative side, we have negative 0.85 here plus 0.7. We have here negative 0.15. So we can see that we have current running on these two resistors. So by project, we can make the transistors conduct a small current even if the voltage is 0 on the input. This is called class AB operation. Class AB operation. We have a small current here that make the two transistors conduct when the signal is 0. This is very important because now let's imagine that we have the positive cycle working. We are on the positive cycle of the signal. When we are on the positive cycle of the signal, the NPN transistor is sourcing the current to the load. The NPN transistor is making the work, is working hard to follow the input voltage on the output. The PNP transistor will start to conduct, but the NPN transistor will stay conducting for a little bit, even on the negative cycle, because even if we have a negative voltage here, minus 0.1 volts, we have here 0.75, 0.7 drop, we have 0.05 volts on the emitter of this transistor. Even with a negative voltage, a small negative voltage, the NPN transistors still is conducting. So now the transistors conduct for a little more than half the cycle. A little more. I will draw the current on the emitters so we can clearly see how this works. Here you can see how this works. In class B, the NPN transistors follow the signal in the positive cycle. The PNP transistor follow the signal in the negative cycle. This is the amplitude, the absolute amplitude of the current in the transistors. So when the NPN transistor is conducting, the PNP transistor is off. When the PNP transistor is conducting, we do not have current on the emitter of the NPN transistor. In class AB operation, the crossover point of the current is over 0. So, when the PNP starts to conduct, the NPN is still conducting a little bit of current. So it never has a point where no one transistor is conducting current. The crossing of the work of the transistors is over the zero current line. Okay? This is the crossover current of the push-pull pair. And we also have the class A operation. How this works? In class A operation, we need to bias the setup with a compensating voltage here that make the quiescent current on the output emitters of the transistors never goes. If in the project we make a circuit that has more biasing current than the current of the load, precisely we need to have I bias greater than I peak over 2. So the biasing current on the emitter resistors need to be greater than half the peak current that will be sourced or synced from the load. The transistors will never cut off and will be always conducting. This is called class A of operation, and it has the lower distortion because we always have the two transistors in the linear region conducting. When the NPN conducts more, the PNP conducts less. When the PNP conducts more, the NPN conducts less. But they are always conducting current and never cut. In class B or class AB operation, you can think that when we have one transistor conducting, we have one active device. When the two transistors conduct for a small period here, a small portion of the cycle, we have two active devices. So the output impedance of the circuit can abruptly change near the crossover point. And this can increase THD performance because we are transitioning from a region where we have one active device, two active devices, and one active devices. Two active devices and one active device. This happens in class AB. Okay? In class B, we have always one active device working on the circuit, and in class A, we have always two active devices. The emitter resistors are crucial for this circuit to work, because if you try to polarize only with the voltage, the circuit will be very unstable and will explode, because the transistor will start a runaway condition where it conducts more current, the temperature goes up, the VBA junction goes down, and it tries to conduct more current until it explodes. So with the emitter resistors, we have margin, so we can program the bias current precisely using the voltage and the resistance of the output resistors. These resistors are called degeneration resistors, and it stabilizes the circuit. We can think of it like a feedback system, because if the current tries to increase, the output voltage here will increase because more current on the resistors will increase the voltage drop on the resistor. So the voltage here will increase and will decrease the VBE, and the output current will decrease. So it makes a negative feedback loop that stabilizes the circuit. Without the resistors, we need a ridiculous precisely controlled voltage here, because think about it. If the voltage drop is 0.7, we need precisely 0.7 volts here. If we put 0.7 to 1 volts, the current will increase a lot. With 0.8 volts, the current will be always 10 times bigger here on the emitter. So it's impossible to do this circuit without the resistors here to compensate and stabilize the circuit. With the resistors, it's very easy to program the output bias current, because now we have a constant resistance here and will generate a linear relationship with the biasing voltage. So guys, this is the circuit we're gonna use to see this working and to see the transition between class B, class AB and class A operation on the bench. This is a very nice and very simple circuit. We have the NPN transistor, is the classical 2222, 2222. Here you have the complementary PNP. The output resistors, I choose 3.9 ohms, a small resistor that worked really fine. We have an AC coupling to the output. This is not necessary, but as we are gonna use this on the 50 ohm input of the scope, if the circuits go bad, I don't want it to burn the front end of the scope. So we can AC couple it. If something wrong happens here, we will not get a DC output current on the front end of the scope. The input comes from a 50 ohm SMA cable and goes to a 5/6 resistor here to match the 50 ohm line that we have from the generator. We will be generating a 1 meg signal, 1 meg sinusoidal signal on the generator. And here we have this very clever circuit here. It's called a VBE multiplier, because this circuit can multiply the VB drop of one transistor to make the biasing voltage here. And we can adjust this biasing with a trim pot here. So I have here 1K, 2K, 1K2, 1K2 here. These voltages will be symmetrical, almost symmetrical, because we have 8 volts here, minus 8 here. We have a constant drop here on the middle, DC, a constant drop on DC. We will see this now. And as we have the same current in these resistors and this resistor here, these points are at the same distance of the ground, at the same distance of the supplies here. This works by a very clever design. So these transistors will try to regulate this circuit to have 0.7 volts here on its base emitter junction, because if the voltage here try to increases, the base conducts more current. If it try to decreases, the base conducts less current. So you get a constant 0.7 volts on this resistor, and this voltage will be multiplied because the current here will be the same current on this trim pot here, because almost no current goes inside the base, almost zero current goes inside the base. So if we have 1K here, we have 0.7. If we have 1K here, we have 0.7 and 1.2 volts. If we have 2K here, the trim pot on the maximum setting, we have 0.7, 1.4 here and 2.3 volts of biasing over the resistors. And with this trim pot, we can adjust on the bench the biasing, and we can see the transition between class B, class AB and class A operation. The signal, the AC signal that comes from the generator are coupled in AC with this capacitor here to this node, and we have this capacitor here that couples the AC signal to the base of the PNP follower. So for the AC signal, for the AC part of the signal, the two bases are tied together here and are going up and down, up and down. But at a DC perspective, they are separated by the biasing voltage. So what really happens is that the upper and the lower base will always be separated by the bias, and the AC signal will make they swing together, up and down, up and down, up and down. If we have zero bias, we have class B operation. If we have a small biasing, we have class AB operation. We can see that here the PNP is cut off, here the NPN is cut off. If we have a very large biasing, the PNP never cuts, the NPN never cuts. The PNP never cuts, the NPN never cuts. Let's see this on the bench. So guys, this is the circuit I assembled here on the bench. So we have here the two transistors, the NPN is here, the PNP is here. The output coupling capacitor is this capacitor here that goes to the SMA cable connector to the scope, to the SMA connector to the SMA cable to the 50 ohm load on the scope. Here we have the transistor of the VBE multiplier, the trim pot where you can adjust the biasing, the AC couple capacitor that couples the input 1 meg signal, and here the 56 ohm resistor that terminates the line with an almost 50 ohm impedance for the signal that comes from the generator. For this video, forget this part of the circuit here. This we're gonna use on the next video. So now we are working only in this region here. This is our push-pull pair. Let's see it working and let's see the transition between the class of operations. So guys, you have this signal generator that will generate a 1 meg signal at, let's see, I think 7 dBm is okay. It's nice to see. Let's turn it on. Here is our power supply that's supplying 8 volts symmetrical, 8 and negative 8 voltage, 8 volts. And let's see the circuit. Here we can clearly see what's going on. Let's see. The blue signal is the input signal. The green is the output, and we can see very precisely that the output only follows the input when the input is over 0.7 volts. Very interesting. We can see that we have 200 millivolts per division. Here we have almost 0.7, 0.5, 0.40, 0.45 volts here. And when we cross the VBA drop, the output starts to conducting, and for the negative cycle, this also happens. If I go to the generator and lower the input, we can see that the output will be almost vanish. Let's see. For the small signals, we don't have output. We have output only when the input signal crosses a VB drop. Very, 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 very interesting. Let's see what happens when we increase the biasing. I start to increase the biasing now. Look at the waveform. Look at the waveform. Here we starting to get in class AB. I think here we are on class AB. The crossover distortion was gone. No crossover distortion. It's like magic. Look at this. Look at this. Very interesting. If I continue to increase, we will start to go to class A operation. Here we are on class AB. And if I continue to increase, we're gonna go to class A operation, and we not see any difference here on the scope, but we can try to probe the current on the transistor, and we're gonna see the transition between class AB and class A. Now we are using two probes to make a differential probing on the output resistor of the NPN transistor, so we can see the current waveform on the transistor. We can see now that we are on class B, operation, and the NPN transistor only conducts on the positive cycle. We can see that on the negative cycle we have no current on the NPN transistor. When we increase the biasing, the NPN current will start to increase. Now we are on perfect class B operation, and I will continue to increase. Now we are entering class AB. We can see that when the signal crosses zero here, we still has a little current. We can increase here we can see precisely. Here we can see that when the output signal green crosses zero, we have current. We still have current on the output of the transistor, and if you continue to increase, it looks like magic. Looks how in class A operation the current on the NPN transistor never goes to zero. The transistor is always conducting. We can decrease the bias. Class AB now operation, we can see that on the time domain here we don't see much difference, any difference between class AB and class A, né? And here we are entering class B. Now we are on class B. The transistor is operating only on the positive cycle, and now we do not have biasing enough to get the voltage to follow correctly. We can see that we have kind of a negative current. This is because the capacitance of the junction that is sourcing a little current on the negative cycle when the junction is discharged through the resistor. So here the transistor is turned off, but the junction capacitance is sourcing a little bit of current. Very interesting. So guys, I hope you enjoyed this video. If so, subscribe on the channel, give a thumbs up for this video, and I will wait you for the next video where you're gonna see this circuit, how it behaves with a very fast edge, how a push-pull pair will behave with a square wave, and how the class of operation changes the edge transition of the wave. See you on the next video.